So today I'm going to talk about. So I'm going to finish boundary conditions, just summarizing a few more things, and then I'm going to talk about variational principle, and give an example of using variational principle. And that's the underlying mathematical approach behind finite element analysis. So I wanted to talk about that, and that will help you to get a theoretical understanding of how finite element analysis works. And it's also quite useful for solving intractable problems analytically, semi-analytically. So boundary conditions. I talked briefly about boundary conditions before. Just want to finish this this part. This you'll have seen hopefully this in electromagnetics class, but it will complete the summary of equations that you should have seen in your electromagnetics classes. So if you have an interface problem, so an interface between two different media, so 1 and 2, so we have 1 and 2, so the top medium could have some conductivity, permittivity, and permeability, and then the bottom region could have a different conductivity, permittivity, and permeability, and then we might have so we have this boundary here, and so we can define a normal to that boundary, n, a normal vector to that boundary. So then so we have to ensure that the fields going from one medium to another is continuously correct. So the tangential, basically just the tangential and the normal field components have to be equal. So in order to ensure that, we have to apply certain boundary conditions. So the electric field boundary condition is defined in terms of the normal component, like this, where this is the normal and this is the dot product, and d is equal to E through the permittivity, and then this here is the electric charge on the boundary. So the difference between the electric field on the two regions can be different by a charge value that could be on the surface of the boundary. So this is the electric charge on boundary, and then the magnetic field they have to satisfy the same sort of normal condition. And so this this should be 0 here on the right, because there is no magnetic charge, but you can mathematically put magnetic charge in. For example, you might actually want to do that. So it turns out, for example, if you have a magnet, you could model a magnet three different ways. You could model the magnet using a magnetization vector in the region. That's the that could then account for variations in the magnetization within the volume. You could approximate the magnet by having current sheet so you could think of this as having a current on the left and right sides. So in this case, the current would be going in here and out here, and then that would create a magnetization, a magnetic field that looks equivalent to the magnet. Then there's actually a third approach. You could apply a fictitious magnetic charge on the boundary. So magnetic charge doesn't exist as far as we know, but mathematically you have the ability to break the laws of physics as long as the resultant field looks the same. It may be useful to model fields using magnetic charge. So in that case, you could make the magnet have a positive charge on the top and a negative charge on the bottom, and then the field would go from positive to negative, just like electric fields. And so then you could model a magnet using charge, and then so in order to describe this charge, you would then set a boundary condition where the charge was non-zero. So you'd be a fictitious magnetic charge here. But quite a few commercial programs don't allow you to do that. You have to do it yourself. Programs like ComCell and in MATLAB you could do it. So this is fictitious magnetic charge. So, I mean, for an example why that might be a good idea, so in 2D it looks like it would be about the same amount of work, because you have on here you apply a boundary condition on the top and the bottom. If you have a current sheet, you wouldn't put dots, you'd define a line and say that line has current going coming out on this line and current going in here, and that would then make this magnetic field. But if you think about 3D, if you have a 3D magnet, then if you wanted to apply the magnetic charge, you would put it and the field was pointing up, you would only have to put the charge on the top surface and the bottom surface. If you use a current sheet, you would have to apply current on four sides going all the way around the magnet to model the magnetic field. So it actually is less complicated to use the magnetic charge in 3D, for example. Okay, so that's just so I like to include magnetic charge in the boundary condition, but just remember that's just fictitious. It's not real. So then, and you certainly can't have a difference, right? You'd have to have the same amount of charge on the bottom as on the top. So that's the normal components, and then we have the tangential components. So these are normal components. So this is the dot product. It gives the normal direction. So the cross product will give the tangential direction. So the tangential fields have to be equal on the top and the bottom as well. And so that can be written out as E1 minus E2 cross product N12 equals 0, and H1 minus H2 cross product equals K, where this is the this would be some current density on the boundary. Current density on boundary. Okay, so I mean that all this is saying is that the field going in has to come out. So if you have N12 here and you have a field going in, then it must come out. And so if you take the angles, the tangential and the normal have to add up, and there can be a difference, and that difference would be described by the charge values or a current sheet that could be applied on the boundary. Okay? Okay. Any questions on that? Okay, so that's hopefully you've seen that those boundary conditions before. Okay, so now, yes.
H2 is the
magnetic field intensity.
In your drawing, you showed what H1 was.
Oh.
H2 is.
Yeah. So H2 cosine is equal to H1 cosine with the angle and sines. So this is just basically saying the sign of the field intensities have to be equal. Okay, so now let's change and start to look at the finite element approach. But before we do that, I wanted to talk about variational principle. So we're going to go deeper into mathematics here. I told you that the first part of this class is going to be quite theoretical. So variational principle applied to partial differential equations, and this is talked about in chapter 4 of the book by Chari, page 143 to 164. In order to do this, I'm going to give equations in terms of the magnetic vector potential, and we'll do it in terms of 2D. So in electromagnetic 2D problems with current, we know that the vector potential AZ can be solved to determine the field distribution. In space. So in space via. So in 2D we would have this equation here. So again, and so if for 2D we only need to solve AZ, because that if you take the derivative of AZ, the gradient of AZ in the x and the y direction, that will then give you the magnetic field components, and then you can calculate force and all sorts of good stuff. So and so this would be true in some region, which I'll call omega. So where omega equals some surface area. Okay. So the variational principle is a different technique for solving problems. And so it turns out that this principle is really good for solving problems in computers. But it's, if you try to solve very complicated problems analytically, I'm being generalistic here, but in my opinion it starts to get really complicated. It can get really complicated quite easily. So it's not as popular to solve problems using the variational principle. But it's really, it turns out to be a really useful technique for solving problems on computers. So, so the basic idea of the variational principle is to, rather than solving this problem here, you could solve that using like separation of variables, or where you make series solution, or what have you. So instead of tackling it using, say, a separation of variables approach, what we could do is solve a different problem that is formulated in terms of an integral. So, so this is equation 1. So what I'm going to say is, so rather than trying to solve this problem, alternatively, we may state the same problem as having some functional, it's called, equal to half del AZ squared ds minus mu naught jz az ds. So, so what I'm so there we'd have a problem that a problem region with some these could be different. This could be a line current. These could be point currents. So we have a region that has some current in it, different places, and we want to know what the field distribution is in this whole surface region, right? So rather than trying to formulate this using directly applying this with certain boundary conditions, what I'm saying is, rather than solve this, let's solve this problem here, but try to minimize the total integral. So we would evaluate the gradient of AZ and square it. We'd evaluate and then evaluate over that integral surface. Evaluate the surface, and then also evaluate this integral, and then find the solution of A, Z, that would give the minimum for this whole thing. so we want to find the minimum of this. So that's the idea. So but then you might say, well, where did this come from? So that's what I'll look at now. So the idea is that U must be a minimum. It doesn't have to be, but you can think of this in some problems, like the one I'm going to give. The equation is the energy, and if you think about it, it doesn't have to be energy, but it's nice to think about it in terms of an energy function. If you think about most problems, the solution will be at the minimum energy point. So this is a way of if you evaluated this, you can think of it as minimizing the energy, trying to find what the solution is for AZ that would give the minimum energy. So U must be a minimum for the correct vector potential distribution. Okay, so that I'm just stating that if you solve that would give you the if you figured out what AZ was, that would give you the answer to the particular problem rather than solving the differential here. But that's not obvious. So let's think about this a bit more. So to see why this is the case, consider the case when AZ, the magnetic vector potential, is not at the minimum value. So for example, consider the situation where, and remember, AZ is a function of space, so it'll be a function of x and y. Okay, I'll write it here, but for the rest of the discussion, I'm not putting x and y, just leaving it as AZ. So let's say that this, I'm going to put an underline under here to denote that's the correct answer. That's the answer. Okay, so this is the true value. But let's say that we add a deviation from the true value. So again, this AZ would be have different values all over the surface. But in this discussion, I'm just going to write it as one variable AZ for the rest of this, because it starts to look complicated otherwise. So we add a little tiny deviation on the AZ. So this is a small deviation from a true solution. Okay, there could be a deviation at each point in general. Okay, so this is the true solution. Now we're saying, well, let's put in a value that's not quite the true solution. So if we put this value into here, let's see what happens. So we'll substitute 3 into 2. So if we do that, we need to look at the first part. So the first part is del AZ. So then the first part will be del AZ squared is equal to del AZ plus this deviation, whoops, squared, which is equal to del AZ squared plus 2 del AZ del n plus del n squared. Okay, if we expand this out. So this last term here is a second order term because it's the square of this deviation. So if this is a small deviation and we square that small deviation, it'll be really, really small. So we're going to neglect the second order effects. So this is second order. Neglect. And so then this here, the second term is the first order term because it's just got the del n. Okay, so we need to keep that in there. And then so that's evaluating the first term in equation 2. And now let's evaluate the second term in equation 2. So we have so the second term is just mu naught Jz Az is equal to mu naught Jz Az plus mu naught Jzn. It's easy. Okay, and I'll call that equation that's 5. It's equation 5, and this is equation 4. So we can put 4 and 5 into 2. So 4 and 5 into 2, and we neglect the second order term. So then then we're going to, I'll put a line under here to denote that's got the that's got the perturbed equation in it. So you know, this another name for this is a perturbation. So so then we have, if we put 4 and 5 into 2, then we have this equation here. Okay, I think that's right. Let me know if you see any mistakes. So this is now the solution. This is now the equation when we've added this perturbation from the exact solution. So then let's now subtract the original equation that did not have that perturbation. So if we If we now subtract 6 from 2, then we will be left with only the deviation from the true solution. So what I mean is, so I'll call it delta U. We have the true solution, we have the solution with the perturbation minus the original, which was 2. And so then if we do that, then this term will subtract out, and the third term will subtract out, and so we'll be left with just the parts with the perturbation in it, just with the deviation. So this one, the second and the fourth. So we have del AZ del N minus mu naught JZ N, like that, evaluated over the surface. Okay, so this, in order for us to have the true solution, then there should be no deviation from that. So then this integral should go to 0. So that it's got this gradient of this n, this deviation, and that, I mean, that is hard to deal with. I mean, this is some deviation which we don't really know. We don't know what AZ is either. It would be better if we could not have the deviation as a gradient term. So it turns out we could get rid of that by using, change that by using integration by parts. So, because you may have forgotten integration by parts, let's just write it out for the 1D case. So if we can note that that del AZ that should be a dot there. Del AZ del N is if you take the gradients of these, you're going to get del AZ del X, and the dot product of it. Sorry, that was missing in there. Should be a dot there. And then so you're going to have del N del X plus del AZ del Y del N del Y. Okay, but but this, like I said, this is not very nice looking, because we've got this partial derivative of this deviation. So we can remove the partial derivative and put it onto the magnetic vector potential term if we use integration by parts. So remember, integration by parts is, so if you recall, if you have two functions, f and g, then you take the derivative of them, then you have you have this, and then you can integrate both sides, and so then I could rewrite this as f g prime is equal to, and so this is the integral of a derivative, so then you just end up with fg evaluated at the boundaries minus the integral of f prime g, like that. That's the integration by parts. So so then if we take a look at this, we've got two parts that have integration by parts, but so let's just look at the first term here. Let me write something. The derivative of a small deviation is deviation, that's the del n del x, del n del y, is difficult to deal with if we use integration by parts. We can remove derivative terms from the n. So consider first term in 8. So this is 8 here. So let's just look at the first term quickly. So we have, if we apply integration of parts, so we have the integral of so in this, I'm doing this in 1D. So in 1D. So in 1D we only have like the x direction. So if we integrate this, we'll have to evaluate it along the x. So we have the gradient, that we have the partial derivative of az, and we have the partial derivative of n. What I'm trying to say is let's get rid of the partial derivative of n and stick that partial derivative onto the az, because it's difficult to deal with partial derivative of a small variation. And there'll be a surprise at the end. So then using so this is the f and this is the g, and so then we'd have az del x n, and then we'd evaluate that from some boundary conditions, and then that would be equal to minus, and so here this term now becomes a second derivative with respect to az, and the n no longer has a derivative on it. Okay, and so then so that's the 1D. If we then in 2D, you can do the same thing. You can evaluate both terms and put them together to formulate the 2D version. So I'm just going to write that out. So in 2D, we would have del az, del n, evaluated over some surface, and then using integration by parts, that would be then the first term would be at a boundary condition at some x and y, and then we have this second term now which has the del squared az in it. Okay, Now, this boundary condition here, so we're evaluating the small perturbation, but if we have some particular problem, it's relatively reasonable to claim that on the boundaries you would know what the answer is. You know, on the far boundary it's going to be 0 or some defined condition. And so this boundary condition, this is evaluated a boundary condition, and so there would not be any deviation at the boundary. We'd know what it is. So for that reason, we can assume that this is 0, that we don't have any deviation from the exact solution at the boundary, because we know what the value is at the boundary. It's a known value. So let's make that 0. So this is 0 since I'll stop in a second. Since in x1, y1 and in x2, y2 assumed 0, i.e. we know values at starting and ending points, then we can now put 9 back into 7. So 7 was this variation. So this was 7. So we can replace the first term with the second term in 9. The first term in 9 is 0 due to the boundary conditions that we said we know. So then we have, so that's a minus there. So then we have remember, so this delta u is the variation. So that's the integral that has the truth. This is the integral that has the deviation from the true value, and this is the true value. Subtract them, and that should just give you the deviated part. And so then we have putting 9 putting 9 back into 7. We have, well, let me write that. 9 into 7 gives del squared az plus mu naught jz n ds, and that's 10. Okay, so n, remember, n is a small deviation from true solution. Okay, and after all of that kerfuffle, we've got this equation now. And if you look, so now if the deviation was 0, then n would be 0, and then this whole thing would be 0, right? If n is not 0, but if this term in the brackets is 0, then we must also have satisfied the condition, right? Because remember what the original problem was. If you look back, equation 1 is written as del squared az is equal to minus mu naught Jz. If you rearrange the term in the brackets and make that equal to 0, this is what you get, right? Because the first equation, equation 1, could be written like this. So what this is saying is that if this is equation 1, if we put this into an integral and tried to find the minimum of it, that would give us the solution. Now, why didn't I just do that to begin with? Well, because this is more tricky to, it turns out when we do the finite element analysis, it's a lot more tricky to evaluate the del squared AZ. It's a lot easier to evaluate the first derivative, because the equation 2 that we wrote down had del AZ squared, which is the first derivative squared. So that's a lot easier to evaluate. So I needed to give this explanation here so that when we get to the finite element analysis, when we have the del AZ, you'll realize that that's okay. If we evaluate that functional, which was equation 2, we'll get the solution the same as if we evaluated 10. Okay, I'll give, so the next part of the lecture I'll give an example where we find the solution for capacitance. Okay, thanks.